Okay, let's look at section 3.4. This section mainly talks about proof by cases. But before we get into it, I would like to go over some terminology. Right? So let's talk about parity. So we say x and y are of the same parity if x and y are both even or they are both odd. We say of opposite parity if one is even and the other is odd. Right? All right, let's talk about proof by cases. It's probably the easiest to just dive right into to an example. Right? Here's the statement we want to prove. For all integer x and y are of the opposite parity, then x plus y is odd. All right? So let's prove that. All right? So first we assume. All right? Assume the hypotheses, right? Maybe I should grab that. So here's the hypothesis, right? So I'm gonna just make a copy. Let's see, make copy, and all right. So here is our assumption, right? We got that. All right. Then by definition, so go here, right? There must be, okay, actually there are a couple cases, right, we need to consider, because x is even and y is odd, and x is odd and y is even. So let's consider two cases. So here, case 1, right, so maybe I should give a little bit of room. Right, case 1, right, let's say x is even and y is odd. Right, so this is the first case, case 1. Then by definition, we know that there exists some integers k and say l, so they're both integers, such that x can be written as 2 times k, 2 times integer, and y is equal to 2 times integer plus 1. Right? Then we can consider x plus y. So x plus y is the same thing as x is 2k, so put 2k, plus y is 2l plus 1, right? Which we can factor out 2 from the first two terms, so it's going to be 2 times quantity k plus l plus 1, right? So we know that, so this implies that there exists, right, some integer. I'm going to use m, which is this guy right here, k plus l, right? Since k is an integer and l is an integer, so the sum is still an integer, such that x plus y is 2 times integer plus 1, right? So therefore, so I'm gonna write it here, therefore x plus y is odd. All right, so this takes care of the first case, and let's look at the second case. So we're going to look at the second case, case number 2. Right? What if x is odd and y is even. All right, if that's the case, argument is actually very, very similar. It's almost identical. So it's k and l, which are integers, such that x can be written as, now it's 2k plus 1, and y can be written as 2 times l, right? So x plus y is going to be 2k plus 1 plus 2l, which is the same thing as 2 times k plus l and plus 1, right? So therefore, there exists some integer m, which is just k plus l, which is an integer, such that x plus y is equal to 2m plus 1, and which gives you the same conclusion as before. So therefore, x plus y is odd, right? So we can actually look at the both cases, and those are the only possibilities. Then in either case, we came up with the conclusion we wanted to conclude. X plus y is odd, and x plus y is odd, right? But as you can see, we feel like we're doing almost exactly the same thing in case 2 as in case 1. So there's a way to not to do kind of a redundant work, right? So here's the special word, right? You can see that in this statement, x and y are interchangeable. So, you can say y and x are of opposite parity implies y plus x is odd. So there's this is a symmetric statement. Therefore, there is no point of looking at these two cases separately. We can do this magic word, right? So you can see that opposite parity just means that the one of them is even and the other one is odd. And in this case, it doesn't matter which one is even or odd, right? So instead of looking at the two cases, we can do this, right? Instead of saying case 1, we're going to do without loss of generality, right? We may assume, right? We may assume this, right? Since it doesn't matter which one is even and odd, we'll just look at the case where x is even and y is odd, right? And the other way is going to be symmetric, so the argument is the same. So we can actually leave out this case 2. All right? Then go through the argument. So without loss of generality, we're going to say x is even and y is odd. Right? Then go through exactly the same argument, and then conclusion is the same. X plus y is odd. And then that's the end of the proof. Right? Sometimes cases are redundant, then we can eliminate some cases using without loss of generality. But to make sure that you feel comfortable using without loss of generality. Unless if you're not comfortable using without loss of generality, you should not use without loss of generality. Just do each cases, even though it feels like you are doing exactly the same thing. All right? That's it. This is the section talking about proof by cases. All right? I hope that this was clear.